Okay, so we took a look at this model here where we show how these nonlinear restraints work. You have this model in the materials that comes with this course called Nonlinear. Go ahead and run that model and then confirm, either by reviewing the video again or on your own, that these restraints are working the way you expect them to. We're going to now go on and take a look at friction in our model. Now, friction is another nonlinear response of the piping system. It's a little more complicated than just adding stiffness or taking stiffness out of a stiffness matrix. Friction resists motion. If there's no tendency to move, there is no friction. But if the pipe wants to move, if the point wants to move, then the friction will retard that motion. It works against the line of action or the response of the system. Now, in the analysis, we either model friction as a pair of restraints which model the stickiness, if you will, of the support surface where the pipe can't slide. So in other words, the tendency of the pipe to move is less than the friction accumulated at that point. Or if it does slip, we do not put the restraints in. Instead, we put a force vector in the model. So if the tendency to move is less than the friction load, we add the restraints perpendicular to that normal load. If the tendency to move is greater than the friction load, a force vector is added to the load case instead of the restraints. Either add restraints or add a force. Now, the magnitude of that friction force can't be greater than the system's push perpendicular to the restraint vector. This vector that we put in for the force is opposite direction of the node slide. If the pipe wants to slide in the positive x direction, we must supply the force of friction in the negative x direction. So we work with stiffness and we also work with the load vector. Now, what's the magnitude of that resisting force, that friction force? Well, it's proportional to normal load. Again, the friction equals mu times the normal load. The normal load is in the direction of the restraint, so the friction force is perpendicular to the normal load. You have to specify the coefficient of friction, mu. Now, this process of iterating for a nonlinear solution will occur for every load case, just like it did with the regular restraints. So you will specify in your input your coefficient of friction. If mu is empty, there is no friction at that restraint. So if the friction load calculated at a point in the piping system is greater than the pipe's tendency to move, the pipe will not move. Instead, we will model it as two perpendicular restraints orthogonal to the restraint vector. So if the restraint is in the y direction, we are going to put an x and a z restraint in your model for that load case. And that's how we have the pipe stick to the support. If the system push exceeds the friction force, the pipe may move. The pipe will then slip as opposed to stick. Here, rather than adding the perpendicular restraints, Procedure 2 will update the load vector to include the calculated friction force vector in the analysis. So friction is doubly nonlinear. Not only do we have to worry about adding restraints or removing restraints, we have to also orient and set the magnitude on a force vector. That sliding path could change from one iteration to the next. So the convergence demands that both the magnitude and direction of the friction load be within a defined tolerance. It's not that tight. In the configuration file, items for change in direction of the slide. If it changes less than 15 degrees from one iteration to the next, we assume that that's insignificant in resetting the force vector to model the friction. If the normal load changes less than 15% from one iteration to the next, we do not find it necessary to reset the normal load. So these are tolerances on these terms. If we put in a stiffness for sticking friction, the value that we specify is this value here from the configuration file, 1.75 e to the 6th. Compare that to 1.75 e to the 12th for translational stiffness for rigids. It's still quite rigid, but not as rigid as an anchor. We also have a value here that's not in use in this model. We'll fool with it later, but we can specify a coefficient of friction. Right now it's set to 0. If you specify a non-zero term here, then in your input, the program will automatically include this coefficient of friction for every new translational restraint added to the model. Changing this value here will not change any existing restraint definitions. This is only for new restraints that you add to the model. So let's go back to our model that we ran a little earlier. We're going to put friction on these 2 plus y supports. Now most people will say, oh, what's the coefficient of friction? It's 0.3. That's typical steel-on-steel coefficient of friction. It's by no means accurate, and conditions change over time as well. So this is kind of a questionable term to begin with, but it's not atypical. Now what about the guide? I have heard a couple different points of view on this. So one, since there is no normal load initially on that guide, there's a gap there, the pipe could actually slide a little bit before the pipe actually engages the restraint in the horizontal direction. So there's no normal load. So there's going to be some free motion before friction starts. So it's very difficult to predict when that occurs. So what I'm going to do is I'm going to say if there's no normal load due to dead weight, some dependable load of that restraint, I'm not going to include friction. Other engineers will have other opinions on that, but I'm just going to put friction on the plus y supports at 20 and 40. What we're going to do is we're going to take a look at the results. We're going to say, well, if I see friction on my restraint, I'm going to make sure it doesn't get any bigger than mu times a normal load, and I want to make sure it's in the same direction against the pipe motion. We want to be able to take a look at with and without friction. This is, I think, a very important point here too. If you're going to run a model with friction, you might be getting some benefit out of that friction's action in the analysis. You can't depend on friction. I would say you should look at every case to see what the worst case is. So we're going to run it with friction and without friction in a single analysis, a nice little feature in Caesar 2. Okay, so we have the interesting issues discovered here. So we're going to run this model again with friction on the 2 plus y supports. We're going to keep an eye on the results, and also in a single analysis run with and without friction. We're going to run the same model we built a little while ago.